Right, good morning, everyone. At least it's morning for me here in beautiful Colorado. Nice day today, but wherever you're at, whatever time zone, welcome, or to those in the future watching the recording, welcome as well. So yeah, thanks for joining us today. We are presenting a webinar on pump concepts, reliable operation, and modeling. Essentially what this means is analyze if your pumps are running reliably and how are you going to get there with AFT Fathom specifically, which is our modeling software. My name is Walt. I am today's presenter. I'm a business applications engineer at AFT. If you've interacted with anyone at AFT, you probably have at least had a touch point with me. So I will talk to customers, do support, sales things, and other business related stuff. So anyway, welcome. Let's jump on in. So today's agenda, we're going to be talking about three things. Okay, first of all, we're going to talk about performance curves. So it might be a little bit of review for some of you, but we got to go through it. We are going to talk about cavitation, what it means, why it's bad. And then finally, we're going to finish with a concept that that brings all like the system and pump interaction together, which is comparing control valves to variable frequency drives as just an example of how to reliably operate your pump. But of course, not just that, we're going to be doing all this modeling in AFT Fathom. So I hope you're ready. Let's get on in. So this is going to be a discussion from the pump user perspective. I have to clarify because this is not about fabricating reliable pumps. That is the job of the pump manufacturers. Rather, this is about how the user puts the pump to work. So not about making reliable pumps, but how properly using those pumps, right? Does this pump work with your system? What changes can you make to your pump or system to make it more reliable? Because most pump problems occur because it doesn't fit with the system. It might have at one point in time, but something changes and it no longer fits, and it's not the pump's fault. Often it's because the system it is in it just doesn't fit well. So this is going to be specific to centrifugal pumps, which means it's operating on a curve. PD pumps is a whole nother topic, but when we're talking about reliability, really those are going to be the rotodynamic pumps. Everything we're doing is going to assume steady state operation. Even though it's steady state, we can still do multiple design cases. So multiple steady state cases, you'll see when we go through it, but again, steady state. And pretty importantly, this webinar is part of a series on pumps and modeling in Fathom. So if you didn't know, we have a pump concept series going on, and this is what they look like. So we've already gone through number one, back to basics. Right now we're on reliable operation modeling, which is the second one. And coming up, we will go through transients and reverse flow. So all of these kind of build on top of each other. So the topics I'm going to go through today assume that you have a basic understanding of pumps, and hopefully the idea is that you would have watched the Back to Basics webinar. So actually, I have a poll for you all, if you can give me a second. I am curious to know how many of you watched the original pump concept webinar, Back to Basics. So take a few seconds to fill out that question. Okay, so it looks like so far we're about half and half. Half of you did not watch it or just joining us, which is totally fine. But I do recommend going back and watching it because we're going to move a little fast through this secondary now pump concept webinar. Okay, great, thank you. So about, if you're curious, 45% of you watched it live and about 10% watched the recording, and then about half, so that's the remaining 45%ish, didn't watch it at all. So great, thank you all for answering that. I'm going to close that. Now, as a second follow-up question to see how effective this kind of series is, I am curious to know if you plan on attending or watching the recording of these upcoming ones, the transients and the reverse flow. So again, the webinars build on top of each other because pumps, as you probably can imagine, complex subject. So it's easy to break it down into digestible chunks. A lot of you say yes. That is awesome. Almost 100%, 97% are saying yes. That is great news. Thank you all very much. I'll give it a few more seconds so we can get the stragglers in. All right, so it remained about the same, 97% say yes. That's awesome. So if you have questions on how to register for these, you can always email us after the webinar. I'll throw some contact information up there, okay? Thank you all. All right, let's get back to the slides. So you can register for those live webinars, 3 and 4 at this time. Of course, if you're watching recordings, the time's gonna be a little weird. Or you can watch the recordings from our YouTube channel, Smiley Face. Some tips though on watching webinars. You can just search our name in YouTube, go subscribe to our channel so you can get updates. Something that's really cool that we decided to do, one of our colleagues recommended, which was an excellent idea, was to break these things up into chapters so that they're digestible, because we know they're longer form content. You might not need everything, but we try to, we're trying to steer you a little bit. So if you go into the description in a webinar, most of them, you will see timestamps, and those are links. So you can actually click those timestamps and it'll bring you to that respective topic. Another cool tip, also recommended by that colleague, is, again, because it's longer form content, you might not have an hour and you just want to get the information. Well, you can run these webinars at 1.25 or 1.5 speeds. I've done both of those and they're still coherent. So you'll still get the gist of the webinar. It'll just come a little faster than the live presentation. So just some tips for you. Okay, now let's get into the first topic, performance curves, or what I call the perf curve. Performance curves, okay. That's a pump curve, right? There's a range of operation. The fact that you're on a curve means there's a range. These curves will have a few different things. They'll have head rise, or, pressure you can think of, power, efficiency, and PSHR, net positive suction head required. That topic was not talked about in Back to Basics, so we're going to get into that a little more here. But the other ones, really specifically head rise actually was in that Back to Basics. So we won't go through too much. But the point is, all of these things are functions of flow. There's not a single point, right? It has a range of operation. And then not just functions of flow, they are further functions of impeller size and pump speed. So you can have different size pump curves, which we'll see because you trim your impeller, and that is typically shown on the pump curve. So with perf curves, there are 3 things to remember. BEP, these are all going to be three-letter acronyms. Best efficiency point, often reported as the flow rate at BEP. So it's the BEP flow rate, BEPQ. That's how we're going to refer to it here. The POR, preferred operating region, that is set by standards, by governing bodies. The AOR is the allowable operating region. That is set by the manufacturer, so different than the POR. This is going to be easier shown, of course, with a graph because we want to look at a pump curve. So here's an example of a pump curve in Fathom. We've used a curve fit, so it's all smooth and all that. And we'll see you don't always have to do a curve fit. In fact, we won't in my examples. But this is to show you what the BEP is. So you have your efficiency curve. What this means is that different flow rates is going to, and this is totally dependent on the pump. Every pump is different. At the point of maximum efficiency, that is what is known as the best efficiency flow, the best efficiency point. It is a single point on the curve. But POR, it's a region. It's different than BEP because you got a point and then you got a region, right? And POR is defined as 70% to 100%, 20% of BEP flow according to API 610. Now, there are other standards that will tell you differently, and it depends on the specific speed of the pump. It could be 80% to 110%, it could be 90% to 110%. So it depends on what standard you are subscribing to. I use API 610 just because it gives a little, it gives the widest region, and I know it's not realistic that you're always going to be operating at BEP. So I like to give a little cushion room, so does API apparently. So this is what that looks like. You have that red dot, which is our BEP, remember, the flow rate. POR is 70% of that. You can be within this range, 70% lower and 20% higher, so 120% of BEP. This is going to be your preferred operating region. You want to operate in here. You want to operate as close as you can to BEP. Then you have the AOR, determined by the manufacturer. Many factors go into this, so there's not really a universal rule. Now, having said that, people do try to make their own standards. They'll suggest maybe 50% of BEP all the way up to like 120, 130. But what seems the most logical to me is talk to the pump manufacturer because they're going to know. But really, it's going to be from the minimum flow rate they suggest, so you're not all going down all the way to deadhead. And then you have an end of curve flow rate where you're running out. AOR should be about halfway between your POR and that runout flow, right? End of curve flow. Does that make sense? Yes, I hope so. I'm talking, you guys can't answer. So here's an example of a real pump curve. This is what I was talking about, that it is, all of these things are functions of flow or capacity, but they're also functions of impeller size, and those are related via the affinity laws. I can't get into those, so watch back to basics if you need to know more about affinity laws. What is shown here, though, that I do need to talk about are the efficiencies. They give almost like a topographical map, right, for each impeller size, giving a region. But if you remember, that other pump curve I just showed you was just a single curve, right? It wasn't like this topographical map. Well, you can still make a curve out of this because you can say at a single impeller size, 65% efficient, lands me at about, what is that, 4, 5, 650 or so. And you can create your own curve, which is what I have done. So this is that same curve digitized. So what I did was I took random points on the curve, made my own curve so that I can save this as an Excel so I can use it for future reference. And I recommend this so you can keep all your pump curves as CSVs or just Excels if you want to do your own graphing. But graphing is easy in Excel, that's why it's good. But you can also copy and paste things from Fathom and Excel like interchangeably, so it's useful. But what I've done is chosen flow rates. That's how I did that efficiency. Here I'm reporting it as a decimal just for input's sake. We'll see in Fathom, okay? But this is these are going to be all the pieces of information you'll need to model in AFT Fathom, because we're not just talking about concepts, we're talking about modeling in Fathom. So here's our example system that we will work through today. It is a single cooling water loop where we're really going to be focusing on the pump and then the system loss, of course. And I'm kind of condensing all of the system loss into a single valve where we're going to compare really high loss systems or low loss systems, right? So I threw in a heat exchanger just to show it's a cooling loop. And yes, we do heat transfer if you did not know. So let's jump in. Here is that model. Right now, we're going to talk about the performance curve group, right? So we are dealing with a cooling water loop. That's great. The pump, though, needs to be defined with that pump curve. So what we're going to do is you can actually copy from that Excel file. So let's see here. I can copy and then paste. Bada bing. You can also import if you'd like. What you got to be careful of, though, of course, are units. So efficiency here, that's why I had them as decimals, because I know I'm going to be using a decimal. And if you remember, you can do a curve fit, or I said you don't have to. That's interpolation. And I want to use interpolation here because I have an NPSH, I have NPSH data, which if you don't know what that is yet, it's okay, we'll get into that. But curve fits don't always work the best. So you can use interpolation, and as long as you're going to be operating in these regions confidently, you can use that. That's great. Okay, oh, I forgot. We need to add information about the POR and the AOR, the different things we mentioned. So because I have an efficiency graph, it can determine what my BEP is, right? That's what this setting is. Here are the different standards for POR. I'm going to use API 610 for simplicity's sake, right? I can specify my end of curve flow, which comes from the manufacturer. And then I'm going to specify my AOR. As you can see, there's no standards. You just enter it in. So what is happening here? My lower or my higher end of AOR needs to be lower than my end of curve flow rate. That just makes logical sense. If you remember, it should be about halfway between the end of the POR to AOR, or sorry, to end of curve flow. Okay, now that we've entered all that, we're going to get more analysis out. So all of the, not all of those things, but the AOR, POR stuff is optional It's not required. It doesn't have blue highlighting like some of these other fields. But just because something's not required doesn't mean you should have put it in, because you get a lot more out of your model if you can. If you have that info, do it. So what we're going to do is we're going to run it. Cool. What I'm interested in is going to be the pump and system curve. So let's go ahead and load it up. As you can see, you can actually save graphs. So if you didn't know that, it's a really useful thing, and we're going to get pretty graphical here with multi-scenario stuff. So what I want to do though now is that I've added my AOR into that pump definition. I want to graph that. I also know that I want to extend my range out. It's going to stop because my operating point's not that far, but I want it to go far. So generate it. So what this is showing me is where my POR region is, like for this specific pump. And you can see we're landing right in the middle. Okay, well, are we at BEP? Where are we at here? Well, we know we're in the POR. If we can also graph this with the efficiency curve so that you get a better idea. Oh, that's the max efficiency. Man, we're operating like right there. Who would have guessed? I'm not going to show it though to save it as part of these graphs, because I'm going to be graphing a lot of things and I don't want to muddy it up. So now that I've added that, I can save my graph for later. Cool. So that's just the system as is. What I've modeled, again, cooling water loop. This valve is going to be my system loss that I play with. Right now it has no loss, a very, very high CV. There's going to be like no pressure drop, right? Cool, but what Fathom is really useful for and why you want to model is because you want to model different things for relative comparison. And that's what the scenario manager is excellent for. So what you can do is create copies, right? And because I changed my parent scenario here, it propagates through the bottom ones. So good, okay, and bad are going to have the same performance curve definitions now. I named them that because one of them is going to be good operation, one of them is okay operation, one is bad operation by varying this valve. So a cool tool is going to be the scenario comparison tool to see what differences are there between my scenarios. So you can choose the scenarios you want to compare. I want to compare everything, but I only want to show the differences. So pretty much in summary, you can see what is different about these scenarios. And you can see, well, it's going to be my valve, right? J9, there's no loss, there's some loss, and then there's high loss. And you can batch run these, which is an amazing feature. And I actually recently learned that you can do it using multi-scenario or use it along with multi-scenario graphs. So you load in the scenarios you want to run all at once. You can then, while it's running, it will generate a pump and system curve for each one of these, put them in a group, and you can graph them all at once. So we can start the run. And it's doing its thing, doing the calculations, right, for each scenario, making the graph. Okay, good. All batch runs completed without errors. Okay, let's get into our graph results. Here is that graph folder, that graph list that I talked about gets automatically generated. We can rename this. Go do the perf curve. You can also name the individual graphs that get overlaid on one another, but because it has a scenario name, I don't really worry about it. So you can load this and you choose what to include. If you remember, the only thing that was different between these scenarios was the pump. So I only need to show the pump information from one of them. But what is different is the system curve. Again, I changed the loss of that valve. And we can graph that again all at once. Because I have gone out so far, my system curve gets really steep. It gives me a really wide range from my y-axis. So I need to adjust that. Boom, easy peasy though. Now what we're looking at is the same pump curve, remember, same POR, AOR definition. So here yellow is my POR and then green is going to be my AOR. The red was my original system, blue was some loss through the valve, meaning more, and then orange here is going to be a lot of loss. That's a very steep system curve. If you need review on what is a system curve, why does it look like this, again, back to basics is going to help you with that. So what does this show us? as you increase the loss, you are moving your pump further and further away from BEP, which is not good. You want to be included, you want to be in the POR and not just in the POR, as close to BEP as you can be. So this can be, maybe a representation of an aging system where, okay, well, my loss is getting rougher and rougher. I mean, obviously it would take many, many years to get to this point, but just to show you can do the multi-scenario analysis and, play with what if scenarios. Well, what if this happens? Do it all at once very efficiently. And of course, you got the legend here, which describes what I was talking about. Now, not only can you do the multi-scenario graphing, we can do multi-scenario output. So what we were looking at was graphical output. Here is tabular output, the same kind of stuff, but as numbers to be exported to Excel or just to see visually. It's kind of hard during webinar for you to look at all this. There are only really two things I want to show you, which will be the applied standards. You can see which standards you've applied to your system. In this case, we only applied a pump standard API 610. And then the pump summary. So this is, again, tabular data about the output of our pump. It figured out from the pump and system interaction that my flow rate needs to be 1,332 gallons per minute. The BEP, based on my efficiency curve, Fathom determined, was 1330 GPM. So we're like right on top of that, right? Of course, that's why I made this. And we're at 100% BEP essentially. Remember from the first scenario, but oh, okay, this is still just one scenario. That's a little boring, right? Let's add in some other ones. Boom. Again, adding the scenarios. Now we can compare. Again, Fathom is powerful for relative comparison. So what is different? Okay, my flow rates are obviously different, right? Because my system curve steepened. My BEP is all the same because the pump's the same. But you can see this percent of BEP gets much and much worse with each operation. And actually, if I go into these other scenarios, you will see warnings that, hey, you actually aren't meeting your standard that you want to meet, or you're operating outside of the POR. I won't go in there because we don't have time. But you can see different things. What I do want to point out here, though, is the power. The original system, what I called good, right? This is the good system, had the most power consumption. Why is that good? Well, like I say, just because something is working harder does not mean it's bad for it. Like work animals, sometimes you push them and that's their happy place. So don't only go off power. And in fact, I have a case study here to talk about. It's not just about working less for each pump. It's about operating at the BEP. That matters more, and because you also get a lot less energy loss. But even though the overall energy is less, you're gonna have problems. That brings us back to the slides. Why do you care where your pump operates? Who cares if I'm outside of BEP? Well, when you're below POR, you get recirculation in the pump. You have reduced component lives. You have higher temperature rise, and these are things Fathom isn't going to model, but it will tell you, hey, you're outside of POR. These are the problems you can expect. If you're above POR, again, reduced lives. You can have high flow cavitation because with higher flow rates, that leads to lower static pressures, and you're a lot more likely to cavitate. That's why the MTSH curve is upward sloping. And overall extra wear and tear on the pump. So there's more problems you will have with that pump, less life you get out of it. So in the long run, it's a lot more expensive. It's not at its optimal operation, right? Okay, so here's that case study that I actually can't go through for time's sake, but there is another webinar that goes through that, and it's called Stop Abusing Your Pumps, They Need Love Too. It is a very interesting case because the client saved $200,000 US dollars a year just by shutting off a couple pumps so that they could run nearer to BEP. So what I recommend is search it in YouTube and again, do one of those tricks to watch it faster or look at the chapters. That's an excellent explanation of just because a pump is working harder doesn't mean it's bad. It's actually good for it. Okay, second topic that I wanted to talk about today, kind of a rough transition, I'm sorry, is cavitation. Don't do that. Cavitation is not good. But before we can really understand why it's not good, we have to understand what it is. Cavitation is the creation and subsequent collapse of a vapor pocket due to rapid changes in pressure. Okay, so what this means is your pump, it has a suction side, right? It's pulling flow through. Well, sometimes, to do that, the pressure gets really low and it'll actually drop below the vapor pressure, cause it to that's what cavitating is, right? It'll start to form the vapor pockets. That's not the problem. The problem is when it collapses and you get this microjet. This is a image about, I think, a valve cavitation, but it's actually the same concept in pumps. So you damage the pump pieces by allowing it to cavitate. Of course, that is going to lead to a lot of problems down the road. It's not reliable operation. So with all those words, what does it mean in layman's terms? Cavitation is bad. Don't do it. Now, how can you determine if your pump is cavitating? That's where modeling software is useful if you can't get out in the field and listen for it. It's not obvious, right? So there's something called net positive suction head. And there are a couple forms of it. There's net positive suction head available. That describes available pressure at the point in the system. That's typically the pump suction, at least in our discussion. It accounts for fluid vapor pressure. Here is the equation. And you might not be an equation kind of guy, but it is helpful to understand the individual terms. So it essentially represents, like, do I have enough pressure at the suction side of my pump so I don't cavitate, obviously relative to what's required. But this is the equation. You have a starting head, like one of your boundary conditions. You have elevation change to get to your pump, and then you have friction to get to your pump. All of that is going to, it could be dropping the pressure, especially the friction if it's high. That all has to be a margin above the vapor pressure, right? Because if it's below the vapor pressure, you're cavitating without any sort of flow. But it's not just enough to be above MPSHA or above 0. And that's because the pump has, internal to the pump, there's even more suction areas. And Fathom doesn't model necessarily those suction areas, but what it does account for is this MPSHR. Sorry, MPSH3, which is used to calculate MPSHR on a pump curve. But MPSH3 formally is the MPSH at which pump head decreases by 3% at a given flow rate. It is a useful thing for experimentation because MPSHA is completely determined by your system. MPSH3 and MPSHR are determined by the pump manufacturer. So what they do is they run tests. Knowing the MPSHA, because it's a system thing, they can see, oh, well, at what point is my pump cavitating? Or at least they determine cavitation because the head rise drops by 3%. The pump curve kind of gets less and less efficient. So informally, this is where your pump is likely to begin cavitating. I say likely because you can't just see that a pump is cavitating unless you have a test rig set up, But you can tell, oh, my head rise dropped 3% than I was expecting. So it's determined experimentally. Well, what you should understand is this all goes into the MPSHR on the perf curve. So this is, again, pump specific, and MPSHA is system specific. The way you know you're not cavitating is MPSHA needs to be greater than the MPSHR, right? And that's what Fathom is really good for. So how does this relate to reliability? Well, of course you don't want to cavitate, that's bad. It leads to problems. Degraded operation, expense for repairs, downtime for those repairs. Not only that though, higher MPSH margin usually leads to higher reliability. I understand there's some nuance to this topic. You don't want too high MPSH margin, but generally you want more margin than you want less. Fathom, the modeling tool, right, helps you understand how your system is behaving with regards to cavitation. So it will tell you what the problems are. You can leverage those scenarios to see, okay, well, what if my tank is draining? How is my MPSHA affected? And is there a point at which I'm going to cavitate? So let's get back into that same model. Okay, but I want to go to my cavitation scenario, right? So here, oh, you know what? Yeah, I wanted to point out we're going to be talking about the pump and specifically the MPSHR curve before I just throw it up there. Okay, so what is different about this scenario now is we are looking, nothing's really different other than I'm specifically calling out this MPSHR data. And if you remember our graph, it slopes upward, and that's because at higher flow rate, that equates to a lower static pressure, and you're just more likely to cavitate. That's why you need a higher pressure required. Okay. So what we can do is, again, check out what is different between these scenarios. Okay, so if you now remember those other slides and the concept about this pump is the same. The pump is the same between all of these scenarios, in fact, except for the VFD, but we'll get into that. All of the scenarios so far and through cavitation, the pump is the same. What is different is I'm changing the system. So in this case, I actually want to change, where are you at? Let's get you shorter. Oh. I don't want to change the discharge side of the pump. I want to change the suction side because that's where cavitation happens. The pump is sucking stuff in. Internal to the pump has these different lower pressure areas. That's where cavitation occurs. So how could I, if I want to trigger cavitation, if you can imagine, my scenario names are good, there's no cavitation, and bad, there is cavitation. I try to keep things simple if you can't tell. If I wanted to trigger cavitation in Fathom, what do I need to do? I need to change some of those terms of the MPSHA equation. So I can start with a much lower pressure. I can have a elevation gain, put this pump up, maybe 10, 20 feet. I can increase the frictional loss through the pipe. There are different ways I can do this. In this case, what I did, and that's what the scenario comparison tool is useful for, is to see exactly what did I change. So in pipe 4, I have a design factor. What this is it'll increase your friction by a certain factor. So when it says 1, it's just using a material database. It's just, that's the roughness of the pipe, it figures out the friction factor. But if you want to have a little bit of a design margin, you can use the design factor other than 1. So in this case, I put 50 times the friction, very unrealistic, but I want to trigger the cavitation just to show you. And not only that, I've also changed my reservoir height. So instead of starting at 20 feet, because that gives me a little more head to begin with, I'm starting at 0 feet. So both of those combined are going to trigger my cavitation. And again, Fathom knows it will cavitate because I have MPSH info here. But also, if you remember, the equation has to deal with vapor pressure. So it's a common question I've had on support. So I'll just call it out here. You need vapor pressure info. If you use one of our standard databases, that will be included by default. But if you have a user specified fluid, you need to put it in because otherwise Fathom cannot calculate the MPSHA. Okay, so let's do the same thing where we're going to batch run. I'm going to change all my scenarios to be the good and bad cavitation. Okay, I want to create the type pump system curve. Don't mind the software collapsing sometimes when it does its calculations. All right. Cool. So let's go back into output. In this good scenario, I want to look at the tabular data for a sec. There's no problem, right? It's the same pump as before. I didn't change really much about the valve. I think I said there's a little loss. But what I've added are some parameters because you can customize your output. What do you want to show? Well, I want to talk about cavitation, so I'm showing MPSHA and R. So what my system is providing is about 50 feet of head to the pump. What my pump needs is about 10, so we're well above, which is great that there's no flags. If we go into the bad cavitation, well, it's bad, right? You saw the meme. You get a warning. You're probably cavitating because for the same reasons, but opposite, your MPSHA is less than what is required. You get a negative margin. And I triggered that by changing the system. The pump was the same. But by changing the system, I also changed the operating point, which changed what my MPSHR is. Again, it's on a curve, right? Okay, so let's go in the graph and let's see if anything interesting happened from this batch. Again, pump is the same, so I don't need to show from both scenarios. Oh, there we go. So what we see is that the system curve steepened, and that's because I had so much friction in the pipe. So this is problematic because not only am I cavitating, I'm operating further away from BEP. So it's kind of a twofer going on. And if I wanted to, again, multi-scenario. None, good, bad. Boom, so now we can see the tabular data. We can really compare them. The good, no cavitation, I was operating near BEP because I didn't really change anything. What I did change was some of the loss, that the valve doesn't have no loss, there's some. But by changing the friction in my pipe, I also changed the operating point. So you can see the MPSHR is a little different. But what's important, again, one of them has a healthy margin, one of them does not. So you're going to cavitate. Fathom warns you, again, how can you use modeling to make more reliable systems? So again, in summary, it was quick to go over MPSH. I'm pretty sure I could do 3 full webinars on just MPSH, so I know it's a little quick, I'm sorry. But what you need to take away is that MPSH available needs to be higher than what the pump requires. Okay, so now our final topic, control valves versus variable frequency drives, VFDs. Hot topic, control valves are like in every system. So let's have them fight, see who wins. So the context, we're kind of like changing a little bit of our mindset. Now we're controlling flow. So in those other topics, we were just letting the pump and system curve interact to find the operating point. But often you have systems you want to control, like you want a certain flow rate, right? You want a certain pressure or something. So when you control the flow, there's really 2 ways to do it. Common theme, right? You can change the system or you can change the pump. So you can change the system losses to get the flow rate you want. That usually comes in the form of a control valve, where it will change the loss to meet a certain flow rate. Or you can change the pump. Usually comes from a VFD, that variable frequency drive, or impeller trim. They kind of do similar things. VFD, I think of more as like a controlling thing. Which option seems better? So again, if all you knew was you can either change the system loss to be higher or lower to meet a flow rate, or you can just change how the pump is operating to get there. What seems better? Supply a lot of energy via the pump and then take it away with system losses by a control valve, or to just only supply the needed energy to begin with. You can tell by the tone of my voice, option 2 is the correct answer. If you have the option, of course, systems get very complex, and the simple model we've been working through just has the one valve. But if you can, it is better to work with a VFD. So what is it about VFDs? Well, they directly alter the speed of the pump. So if you know your affinity laws, and again, not back to basics, we know that decreasing the pump speed collapses the pump curve. It just kind of drops it down, also shown, better shown with the graph, which we will do. There is less power consumption because of that, because power is H times Q. So what that means is, I'm gonna pull out my little pencil real quick. So this is, let's say that's 100% speed. This is 90% speed. Oops. And this is 80. So by just changing the speed of the pump with that VFD, you're collapsing the curve, right? Why is that good? Well, you can essentially think of power as H times Q with some conversion factors, of course, in accounting for efficiency. But if power is my head times my capacity, you can imagine, let's see, if I'm operating right here, the area in here is much less than the area at a different, or sorry, with a larger pump curve, right? So because my area is much lower, you actually have less power consumption, but it makes sense, right? You're adding a whole bunch of power and then taking it away with the control valve, or you can just not add a whole lot to begin with. So let me clear that out. Okay, so, and when you're collapsing the curve or changing the speed, you also change not the efficiency percentages, but like where that happens, because now you have a little bit of a different BEP flow rate. So I just color coded them for visual sake. Oops. So what do VFDs do? Well, they avoid another point of failure in the system, because control valve cavitation is often a concern. It's a kind of a hot topic. Well, if you don't have a control valve, man, you got no cavitation to worry about, because you're not trying to control the flow too much. Of course, again, you're always going to have control valves, but they don't have to control it as much. It can be shared. And as opposed to trimming impellers, again, if you remember the affinity laws, trimming impellers also collapse the curve. VFDs are flexible to meet different flows as demand changes. Trimming impellers, man, you're kind of like, they're a little more permanent. Can't exactly extend them out if you need a higher flow rate and all that. Lower speeds tend to, but not always, increase NPSH margin, which leads to higher reliability. That is not always true. It depends on the system, and NPSH doesn't follow the affinity laws like the others. It's really like, it's totally just experimental. There's no theory really. You can assume different things, like it kind of follows some similar things as flow, where it's a function of, or it's a function of the ratio squared. That's the way it works for head. Sorry. Anyway, it just doesn't have its own thing with affinity laws. So it's not always, it really depends on the magnitude. You have to do your own analysis, but typically that's a rule. Oh, well, that's all great. Why doesn't everyone use them? They're more expensive, man. That's kind of expensive to get a pump in the first place. Now put a VFD on it. But utility companies will often offer rebates for VFDs as a sustainability initiative. Gotta love the government. So there is incentive to do this. You gotta check with your local utility company, of course. So let's get into Fathom. Okay. All right, back in Fathom. Can collapse that. Okay, now we're in the CV versus VFD. What I've done here is I've taken that manual valve from the other scenarios, and I've just turned it into a control valve. So I want to control it to be this flow rate, 1,150 gallons per minute. And that's with my CV on. With my CV off, this valve is actually providing no loss. You can have an optional condition where you don't have any loss. You'd be like, well, why would you even put the control valve in there? Well, it's because it's easier to manage scenarios that way. You know, if I just got to simply turn it off. And instead, my pump is the control point, right? It is being controlled to that flow rate. And what Fathom will do is vary the speed of the pump until it meets that set point, and it will report back, you know, what speed it was operating at, the power, all of that. So just to confirm, I want to check my scenario comparison tool. Awesome tool. Let's see what the differences are. So because I'm in my control valve scenario where the control valve is on, it comes up first. There's nothing weird about the pump, right? It is NA, no pump control setting. It's at 100% speed, pump's normal. Control valve though is on. There's no special condition. That's why it says none for special condition. The special condition for my other scenario where the control valve is off is it's fully open, it's not actually controlling, and then my pump is controlling. So you kind of like see how we crisscrossed them, and we're gonna let them fight it out. I left the reservoir and pipe friction as our original performance curve version because I don't want to cavitate. That's not the point of this one. But again, I can batch run, right? Add scenarios, okay, redo which ones. I want these control valves, and I want to make my pump and system curve. I don't know if I mentioned where this curve comes from. This appears because I had made that one already as my first pump, and it can take that template and make it for every scenario. So you need a template first. Oh man, it's got me, actually it's good to talk about this. Okay. So if you've ever seen a reference pressure issue, what this means is you can't have two flow rates defined in a row because it doesn't know what pressure those are operating at. It's kind of cut off, so you get a reference pressure issue. So what I need to do, it won't develop a system curve, because to develop a system curve, it's running a bunch of flow rates. But if I am controlling the flow, it doesn't really know what to do. So what I need to do is actually model this without the control valve. What this does, that's not what I expected. Let's see. Okay, well, it's kind of glitching out on me, I'm sorry, but that's why I have a slide for you. So what modeling without the control valve does is it will give you the system curve ignoring the control valve. So this is where it would operate if there was no control, right? But because there is a control valve, it stops the flow, and this extra pressure loss is what the control valve does. So you can see here between my two scenarios, now the system curve hasn't changed. It's the pump curve that has changed, but they're operating both at the same flow rate. So the control valve topic in graphing is very confusing. It's because really to generate a system curve, it assumes many different flow rates, but like you got a control valve, so there's not really many different flow rates. There's one flow rate. So you model it without the control valve. If there's a single path, you have to do that, in fact. And right here is where that will operate. So you have to know what your flow rate is, and you can assume the pressure loss there across the valve. So sorry about the graph. I'm sure there's something I'm doing wrong, but that's also what graph or tabular output is good for, especially that multi-scenario stuff. So let's just get into multi-scenario. Oh, it's not running at all. Oh, I'm sorry. Do I have a VFD defined as well? No. Okay, let's see. Maybe I can get this back on. Yeah, okay, wigged out a little bit. Well, now let's see, maybe it'll, the graph will work. Oh, no, hold on. Give me a second. No, still not good. Okay, well, again, ignore me. But now at least we got multi-scenario output. This is the problem with doing things live, huh? Okay, so what we're looking at are the two different scenarios where I've got a control valve or I've got a VFD. Both are controlling the flow rate. So that's what I was getting at with that graph, was we're at the same flow rate, right? So the system is still meeting your demand. So as far as you can tell, you're like, well, yeah, why would I care which version? I'm getting the flow rate I want. Two things are going to be power and then VEP. So we will look at overall power, which accounts for efficiency. So again, when you're using a control valve, you're adding a whole bunch of power to your fluid. And then you have to take it away with that control valve. That's what that little pressure drop dotted line I was showing was on the slideshow. Well, if you just collapse your curve to begin with, you're using way less power. Now, in this case, also, it's a kind of one of those double whammies where not only are you using less power, you are actually closer to BEP. And that just happens to be this case. So I'm not saying that's always the case, but kind of showing how useful Fathom is, because you can get all of this kind of at a glance. Multi-scenario is by far one of my favorite features of the software. So in the long run, you can also calculate costs. So in these different scenarios, what I've done, oh, I guess I did not. Yes, I have. Okay. There are cost tables. So I have actually added in electrical cost, and it will give you a comparison of what is the cost of this system versus the other one over a certain amount of time, well, you can see you're saving you can actually put a dollar sign to it. How much money are you saving over time by accounting for the time value of money, the hurdle rate, inflation rate, all of that. Fathom's pretty sophisticated. And then you can come up with a final answer of you're saving money. Maybe not useful for an absolute number, because obviously you've got specialists who deal with economics in your company, but it's good for relative comparison. So you can see, well, I'm saving money. That's what I care about ultimately, is that I'm saving money. So when we ask the question control valve or VFD, fight, who wins? The VFD wins. Okay, so now we get to the summary and conclusion. What do you actually take away from this prez? You want to operate near BEP inside of the POR, and all of that you can specify in Fathom. The BEP will come from your efficiency curve or power curve. If you remember input, you don't need both. You just need efficiency or power, and that's because they relate through the H times Q, so you only need one or the other. But anyway, you can get BEP, specify POR in your pump configuration. And use Fathom to test different things, like your system aging over time, which I modeled with just having a valve be tighter and tighter. But that's the power of that. And this was a very simple example. I had 3 scenarios, right? You can imagine, you can get a lot of scenarios going. What I would call then the sensitivity analysis, where you run multiple scenarios, batch run them, and then use multi-scenario functionality, which is the graphing, and then the tabular data, the model, output to compare results. And other software, I've seen do sensitivity analysis, but I tell you what, I've never seen software that can have full-on different scenarios, because with scenarios, you can change a lot more than one parameter, right? You can have very different things. And Fathom is amazing for that. I remember any other engineering software I'd have to use, you make multiple model files. Well, in Fathom, you just have one file with multiple design cases. And that, I guess that applies to our other conditions as well, but we started with the perf curve. Second thing was, don't cavitate. Keep a healthy MPSH margin. We saw that it is the suction side definitions that's going to change your MPSH-A. If your pump is the same, that's going to be what causes cavitation. You want a healthy margin. So again, what scenarios are useful for is comparing different operating conditions. You want a healthy margin. To calculate cavitation, or for Fathom to detect it, you need both the MPSH-R info in your pump curve, and you need fluid vapor pressure. Again, the fluid vapor pressure is often overlooked, because if you just use your own user specified fluid because you know the properties, you forget to put in vapor pressure, it's not going to calculate it for you. Finally, VFDs are superior to control valves. If you have the option, again, I know obviously mine is a very simplified system, but again, it shows you the idea. If you can use a VFD in your system, it's going to be much better for you in the long run. And you get that rebate, so you don't have to worry about the cost. In Fathom, how you do it is you go to the variable speed tab in Fathom pumps for modeling. Lower power, less money, along with other benefits. Mr. Cool Guy shows up. Okay, so let's talk about some resources to keep you sharp. We have a great tips and tricks blog. Sometimes it gets buried because maybe they're a little old, but they're all so good and so relevant and easy to understand. I highly recommend them. So you can go on our website, Learning Center Tips and Tricks blog. If you're confused, I guarantee you someone else has been. Probably even an AFT employee has been confused, and so we decided to write a blog on it. We've got more webinars. I mentioned, of course, the pump series, or the pump concept series that's coming up. You can always register for those. Go to Learning Center webinars, upcoming webinars to register, or you can go to the webinar library to watch them, or of course YouTube. It's a little easier, I think, through YouTube personally, I believe. And then finally, inside of the software, we have a great help file that is searchable, that will help explain concepts, but also if you're new to the software, walk through some examples. They are really good. And I know it's intimidating, like I don't want to go into a help file, I don't want to walk through examples, I just want to know. I just walk through them and you will be set. So thank you so much for your time. Here's some contact information that I promised. So email, sales, or support, depending on the nature of your question. Though that is the phone number 719, beautiful Colorado Springs. This is where I'm sitting right now, and that mountain in the background, Pikes Peak, beautiful view. Now you might be wondering, well, how can you see the mountain if this looks like the backside of the building? Well, you're right, but we also have all the other offices, so we get to see it. Anyway, we're all local here in Colorado, so you can call our number during business hours. We're going to answer. That was the point. So thank you all again. Happy engineering, and please don't hesitate to reach out with any questions, okay? Thank you.